In Chapter 14a, we talked about the basis of how weather information is gathered and how it's analyzed, and a little bit about forecasting. In B, we focused on numerical weather prediction and different methods of forecasting. And in 14C, we'll talk more about long-term weather and climate patterns. And one that is often made reference to, especially here in California, is one that's called El Nino. So here's the story. This has to do with what goes on in the waters off the west coast of South America, specifically in the eastern Pacific Ocean near the equator, from about Ecuador down to Peru, especially Peru. Typically, there is a cold water current which comes equatorward from south to north toward the equator from Antarctica along the west coast of South America. It's called the Peru or Humboldt current. This is a cold ocean current, much like our California current, which comes from the Gulf of Alaska from north to south. This is cold, nutrient-rich water, which actually provides a tremendous fishing industry for the country of Peru. Now, occasionally, near the end of a calendar year, like say November, December, a warm current of nutrient-poor water moves poleward, I should say, from the equator, which displaces the colder water. Now, whenever that happens, this is the setup for what's called El Nino, because it seems to happen around December, so the locals call it El Nino. They've called it that for centuries, or the boy child, referring to the Christ child, because it's around the Christmas holiday. Usually, the ocean water warming lasts for about a few weeks, but if this ocean water, this anomalous warming, which replaces the cold, nutrient-rich water, lasts for several months, the economic results to the Peruvian fishing industry can be catastrophic. Fish die or fish swim where the water is colder because the water's gotten too warm. Weather patterns can change, so it can be quite disruptive if it is a particularly intense episode and lasts a long time. This El Nino scenario occurs, this unusual warming of the eastern Pacific equatorial waters near Peru, occurs in rather irregular intervals of 2 to 7 years, and scientists do in fact call it El Nino. Now, in a typical situation, which is the graphic you're seeing now, high pressure, which is associated with cooler water, controls the weather in the eastern equatorial Pacific, as shown on this little map. And low pressure, associated with warmer water, usually controls the weather in the western equatorial Pacific, i.e. Indonesia. And this is the typical non-El Nino condition. This tends to result in dry conditions near Peru. In fact, southern Peru and northern Chile have some of the driest desert areas in the world. And that also is conducive to wet conditions in Indonesia. Again, 14.14a is the typical non-El Nino condition. When this condition reverses, it results in wetter conditions than normal in Peru and drier conditions than normal in Indonesia. In that reversal, which is now shown in 14.14b, an anomalous strong countercurrent, in other words, a current of ocean water moving west to east, brings the warmer water to the Peruvian coast, making it wetter than usual there, because now the water is warmer, therefore the air adjacent to the water is warmer, and clouds can form. Meanwhile, just the opposite occurs over toward Indonesia, where now they have cooler than normal water, which is associated with drier air, which means their air is sinking, not rising. So they have the opposite of what they normally experience. And Peru has the opposite of what it normally experiences. So after a year or so, this pattern does reverse and returns to normal. So it's often called El Nino Southern Oscillation, or ENSO for short. Now, there's a thing called La Nina, which is just the opposite. This is when the normal conditions in the Pacific with the cold, nutrient-rich water become much colder than usual near Peru and much warmer than usual near Indonesia. This is called La Nina. Sometimes a quick reversal from El Nino to La Nina can occur within a year's time. Figure 14.15 actually depicts that. You see strong El Nino conditions in December 1997, and then strong La Nina conditions just a year later, where the equatorial Pacific has cold sea surface temperature anomalies. These are departures from normal. These colors, that's what they represent. Recent major El Nino events that have had an impact on California with excessive amounts of precipitation include the winter of 1968-69, the winter of 1982-83, and the winter of 1997-98. All of those, by the way, were very wet rainfall seasons for California in general, and actually Fresno in particular. If you want to know what the 3 wettest rainfall seasons are on record in Fresno, they are number 1, 1982-83, number 2, 1968-69, and number 3, 1997-98. Sorry for the graphic being in the middle. That's not how I composed the slide. The Ocean Nino Index shows you warm event and cold event events, that's kind of redundant, in the equatorial Pacific. These are 3-month running means from in terms of the departure from average over the tropical Pacific Ocean from 5 degrees north latitude to 5 degrees south latitude, and from longitude 120 west to longitude 170 west. Warm El Nino episodes are in red, and cold La Nina episodes are in blue. So if you look at this graphic, which is courtesy of Noah and Jan Null, who's a friend of mine, he's a certified consulting meteorologist in the Bay Area, you can see that a big El Nino was in 82-83, and another big El Nino was in 97-98. Now, it doesn't always translate this way, but here are some general weather patterns which can result. If there is an El Nino present, especially in the winter time in the northern hemisphere, it can mean wetter than usual conditions in the southern United States and northern Mexico, and warmer than usual conditions in the northern part of North America. If a La Nina persists in the winter, it can mean cold and relatively wet conditions in the Pacific Northwest, and how far south that extends is kind of dicey, because you see the bottom end of that green shaded wet area is just about down to Fresno. And it can mean wetter and warmer than usual conditions on the East Coast, and drier and warmer conditions than usual in the southern United States for a La Nina winter. And these things vary. They're not always like that. Here is a graphic that shows regions of climatic abnormalities associated with El Nino during December through February, okay, and the kinds of conditions that may apply. And the next slide is regions of climatic abnormalities associated with El Nino during June through August. So you can see the kinds of effects that happen December through February in an El Nino. You can see wetter than normal in the southwestern United States, December through February, in a strong El Nino or ENSO. And then, interestingly, you see warmer than normal conditions in the west coast of South America during June through August. So it depends on where you are in the world. Then there's another pattern called the Pacific Decadal Oscillation, the PDO, implying that it happens every decade or so. This is based on research done at the University of Washington, and they identified another long-term Pacific Ocean temperature fluctuation, which has a warm phase and a cold phase. The warm phase tends to bring storms into Alaska and California, but leaves the Pacific Northwest dry, which is kind of peculiar, kind of a split flow, you might say. And then the cold phase tends to produce wet weather in the Pacific Northwest and dry weather in the south. So here are the maps that are part of this Pacific Decadal Oscillation. The warm phase, once again, storms to Alaska and California, but dry in the Pacific Northwest. And then cool phase is the one on the right, which tends to bring wetter weather to the south. There's another fluctuation in the Atlantic, which scientists have discovered or quantified, called the North Atlantic Oscillation. This is a function of changing pressures between the Icelandic low and the Bermuda high. The positive phase of the North Atlantic Oscillation is when pressures fall and get lower over southern Greenland, and pressures rise over the Bermuda high. When this happens, this tends to strengthen the westerlies embedded in the jet stream and tends to make northern Europe a lot milder than normal and a lot wetter than normal, with wet winters in the eastern U.S. This is the positive phase of the North Atlantic oscillation. The negative phase of the North Atlantic oscillation is when pressures rise and the Icelandic low gets weaker, and pressures fall and the Bermuda high, which gets weaker. And this tends to make southern Europe wet and mild and northern Europe cold and dry. So that was a little bit about the North Atlantic oscillation. There is yet another pattern in the northern hemisphere that scientists have discovered, which is called the Arctic oscillation. This is closely related to the North Atlantic oscillation that I just showed you, but it has to do with changes in pressure in the Arctic region and regions to the south and what happens. So if pressures get lower in the Arctic, this is the positive phase of the Arctic oscillation. This tends to produce strong pressure differences between pressures in the Arctic and pressures off the west coast of Africa. That tends to produce strong westerly winds, which tend to prevent bitter cold air from reaching the United States. You see the U.S. is shaded in rather mild conditions there in the positive phase of the Arctic oscillation. In the negative phase of the Arctic oscillation, this is a cold phase, which tends to mean that pressures are higher over the Arctic, and there are weaker pressure differences then between the Bermuda high and the Arctic high, and that allows for cold outbreaks in the wintertime in the winter, and cold outbreaks in the winter in the United States, I should say, and also colder and drier weather than usual over northwestern Europe. So this is the negative phase of the Arctic oscillation. This ends PowerPoint 14C.